So this time we're going to look at points of inflection and the intervals where the function is concave up or concave down. All of this g of x. So I'll copy this. We use up a whole page doing part A and B. So I will add another page so that we can now answer part C and D. Now these problems are pretty lengthy, right? All right, let's do the point of inflection. So find the first derivative, which is 20x cubed plus 60x squared. But don't stop there because point of inflection and concavity is all from the second derivative. Take the second derivative. Now that's what we're going to use, okay? Set this equal to 0. You need to set this equal to 0. I will factor out 60x to the front, which will get me x plus 2 in the parenthesis. And now we're going to set each of these factors equal to 0. So when is x equal to 0 or 60x equals to 0? Well, here's our first potential point of inflection. Okay, you know I'll call it potential, right? Because if the concavity doesn't change at that point, that's not a point of inflection. These are just our candidates. So we got our two potential points of inflections. So sketch a number line. We're going to have to check the sign of our second derivative around these points of inflections. So I will put 0 on the right because that's bigger. I will put -2 on the left because that's smaller. Now what we have to do is plug in to the second derivative. Okay, so that's the second derivative. Let's plug in some numbers to the left and right. So I will pick x equals -3 because -3 is smaller than -2. 60 times -3 times -3 plus 2. This is 60 times -3 times -1. Positive times negative is positive. So this section is concave up. All right, let's go to the middle one. I will pick a number that's in between -2 and 0. -1 is right in the middle, right? So if I plug in -1, I will get 60 times -1 times -1 plus 2. That is 60 times -1 times +1. Well, 2 positive and 1 negative multiplies to be a negative number. So this is concave down. Oh, look, concavity changed at -2. This is our point of inflection. We found one point of inflection. I shouldn't really call it point yet because it's just the x coordinate, but you know what I mean. We'll find this y coordinate later, okay? This is where things will change though. Now let me do the last one. A number that is bigger than 0. I'll do 1. If I plug in 60, I'm sorry, not 61 into the second derivative, I will get 60 times 1 times 3. If I multiply 3 positive numbers, I will get a positive number. This interval is concave up. Yay, look, the concavity changed at x equals 0. This gotta be point of inflection. So let's write down our answers here, okay? I will say this graph is concave up on -2, -infinity to -2, union 0 to infinity. Now, in between those two, though, we have that interval where we have concave down. So I'll say concave down on -2 to 0. And we have 2 points of inflections. Points of inflection, the first one is at -2. I don't know the y value. And 0. And sorry, I don't know the y value. Let's go find the y value. So, all right, gotta go back up and find the original function. This is the original function. We need to plug in our x's into this original function to get the y values. So here, oh, I think we did it already. When we plug in 0 into the original function, I got 0 out. So the first point of inflection that we got is 0, 0. Okay. Now, what will happen if I plug in -2? Oh no, let's do it. -2 and -2. The second point of inflection is at -2, -80. So, I don't know if they ever ask us to sketch a graph, but we really have enough information to get a very good sketch of this function. Let me go back up to the problem. Look at all that work that we did. They never really asked us to sketch a graph, but we can at least try to graph the original function and see if it has all the features that we identified. Okay, so I will graph that function here. So here's the graph of our function. That's the picture that I thought. And I think it's just was the lowest point. So the relative minimum, hold on a second. Am I graphing? No, I don't think so. Let me see. No, I didn't graph the right one. So I gotta change this to 20. All right, now that's gonna be good. All right, so let me zoom out. So that's the picture. Wow, it goes down pretty deep. I'll change the y-axis down to like -100. One second. Or maybe even big. All right. Look at this graph for me. So that's my sketch. Something like this. I think it kind of looks the same, right? Let me click on this point. We have a relative minimum down at -3, -135. Let's see if I have that. Do I have a relative minimum at -3, -135? We do. So that's good. There was another critical point at 0, 0. But that is neither a relative minimum or maximum. It's hard to see the concavity of this graph because it's so squeezed. So, but maybe if I can change the graph setting, let me try that real quick, okay? All right, so I will plot our points of inflections here, okay? 0, 0 is the point of inflection, and another point of inflection is -2, -80. All right. All right. Did the concave, all right, so do you see like a smiley face or the mouth of a smiley face to the left of that point? Definitely concave up, right? And another kind of U shape from 0 to infinity, concave up again, half of a U shape, yeah. But this point from this -2 to 0, this is upside down, right? Upside down U. So yeah, I think I can see it's not really the most beautiful picture to read concavity, but we'll do more picture reading on the next page, okay? But this example was another gigantic one where we had to find all like special parts of this graph. And in this video, we focused on points of inflection and concave up and concave down interval by working with the second derivative.